All right. Hi, everyone. My name is Romain Guy, and I work at Google. And I'm going to talk about physically based rendering and how to mitigate aliasing issues, especially in the context of VR. So this is not something I usually talk about. This is pretty much a hobby of mine, so not related to my work. And this is the first time I've ever presented on that topic. So if things are not clear, feel free to interrupt. I will try to answer all your questions. There will be just a little bit of code, quite a bit of math, and hopefully a lot of pictures and screenshots and demos. But before we get started, I just wanted to let you know that today is the day that one of my favorite games ever was released. And I'm here instead of playing the game. So you should be approved that I really, really wanted to talk about this with you tonight. There's a Tentacle. You should go play it if you've never played it. So how many of you are familiar with physically based rendering? What it means, what it is? 2, 3 hands? Well, I guess people from Autodesk should be. So there are many descriptions available online about what PBR is. So this is something I wrote in an email. So physically based rendering is a method that provides a more accurate representation of materials and how they interact with light. So really the idea is to be able to separate the definition of a material from the lighting itself. And it allows to have materials that are more consistent in all lighting environments. It also makes it easier to create libraries of materials that are plausible, that looks good. So even for people like me, I'm a programmer, I'm an engineer, I'm not much of an artist. With PBR, I'm able to create scenes and materials that look reasonable. So this is a huge step up from what we've seen, especially in games and different 3D viewers over the past 30 years or so. And I'm talking about real-time renderers, real-time viewers, not offline renderers. So physically based rendering, there's not a single way of achieving it. And so that's why if you go online and you try to understand what PBR is about, it can be very confusing. It's more a series of concepts and ideas or principles that you will want to follow when you implement a rendering engine. And thanks to a great paper that was published in 2012 by Disney, so the author was Brent Burley, PBR has really gained popularity amongst real-time renderers. So that paper was about how they implemented physically based rendering for their offline renderers that they used in Wreck-It Ralph. And all the techniques I'm going to talk about are basically work in real time. I'm going to show you a WebGL demo. And they've been used, and they are used today in movies. They have slight variations, and they're slightly more complicated. They make less approximations, but really the ideas are the same. And all modern game engines really have moved to PBR. So Unreal 4, Frostbite 3, Unity 5, and tons of different tools that are helpful to artists and designers. So some of the tools that I use quite often, Marmoset Toolbag, Substance Designer, and Painter, they're all PBR based. So if you do move to PBR, if you do implement PBR in an engine or use a PBR engine, it's fairly easy to create materials that will work in other engines, and you will easily find a series of tools that will help you create the right assets. So here's a series of a list of concepts that I've been following when implementing my own PBR engine. So we're going to talk about conductors and dielectrics. If you don't understand what that means, don't worry, we'll talk about it. The microfacet model. In the PBR system, you want your lighting to be energy preserving. So that was a huge flaw in a lot of games, especially until very recently, where the amount of light reflected off of the surface of an object was sometimes greater than the quantity of light that was hitting the object in the first place. And that's how you ended up with lighting that didn't feel really good. You could see that in games where the character is somewhere deep in a cavern, and it almost looks like the character is glowing, like emitting light, because they're not following the energy-preserving concept. We're going to talk about image-based lighting. This is a technique that's been common in the movie industry for a long, long time. It's now accessible in real time. Linear lighting, we'll skip that. Area and photometric lights, those are wonderful, and I could talk for hours about them, but we're going to skip that as well, and physically based cameras. So these are just to give you ideas of what topics you could research if you were to dig deeper into the whole PBR thing. So to give you an idea of what things can look like, so this is a demo I wrote for the Android Dev Summit back in November. That was to demo something completely different. That was to demo a new feature of the IDE. And this is a Java application running on a Nexus 9. So it's all Java and OpenGL ES 3. And this utilizes all the concepts I just talked about. So everything here that you see is physically based. It's all dynamic. So the shadows are dynamic. The lighting is dynamic. Nothing is pre-baked. And I was able to come up with that demo in just a couple of days. I don't know how to model. I just bought a few models from a website, like I bought the chess pieces. I was able to create the metallic, the gold, and that iron-looking material on the other side myself. And now I'm going to show you another demo. So that one is a WebGL, basically playground that I use to investigate. So I'm sorry, like I want to apologize because until last week I didn't know I would be giving this talk. So the demo is not particularly impressive, but it gives you a fairly good idea of what PBR can do for you. The screen is pretty bad over there. It looks better on my computer. But you can get an idea. So everything that you see here is running with a single shader. So all the materials are using the exact same shader. So I'm not playing tricks. I didn't write custom code to be able to render bricks or metals or anything. So we're going to focus on this object here. So here we have a sphere made of concrete. And if I change the textures, I can then create bricks. Let's see, brushed copper. And again, it's all the same shader. We're not changing anything. We're only changing the textures that are being applied to the object. And as you can see, like they all feel like they belong in this lighting environment. I can do wood. It always works. That the lighting changed, the object still looks good. Or if I go in a darker place, you can see that the environment is lighting the object. So on this side of the world, it's pretty dark in the back. So you can see that the object is in the shadows. And there's a strong light in the background, and you can see like lighting the object on the side. We can try another one, like this industrial room. Let me change let's see this one. So here we have neon lights on the ceiling, and you can see them being reflected on the metallic object. And again, we don't have to change the assets. We don't have to change the lighting rig. Everything works because we've separated the properties of the material from the lighting. So when I change the lighting, everything still works. We can, of course, use more complex objects. Let's see, for instance, my camera. It takes a little bit of time to load. It's I think 2 million triangles. It's pretty heavy. So again, a complex object. And if I change the lighting environment, you can see how it affects the rendering of the object. And always feels like it belongs in that scene. So this is, I think, an office at Google somewhere. Another interesting object, a car. The great thing about PBR is that because the material system is so powerful, we can create really complex-looking objects like this one. So this is a car, and it has 2 layers of paint on the car itself. And this object here is not using a single texture, so it's using only single colors that have been applied to different parts of the car. But by manipulating different properties of the material system that we'll talk about in a few minutes, we can really create a convincing image. And we'll get back to this demo later. There's a lot of other things that we can look at if we have time. All right, so first we're going to talk about a little bit of math. To create that demo, I've been reading hundreds of research papers full of equations, and I still have nightmares just thinking about all those equations. Sorry. So first, let's talk about the VSDDF. So how many of you are familiar with the terms VSDDF, BRDF? Okay, either you're all dead or you don't know about it. So it means bidirectional scattering distribution function. It's a very fancy name, and this is a VSDDF. So the gray part here, imagine that it's the surface of an object. That's really the material itself. You have the yellow line, that's the light incoming, and it's going to bounce off of the object and send light back to your eye. Some part of the light will enter the object, so there's going to be refraction that you probably remember from your physics class. Some of that light inside the object, it's not shown here, will be absorbed and scattered. We'll look at that in a minute. And some of the light will go through the object on the other side and be reflected out. So this act of coming out on the other side is called transmission. And this is something that you see, like for instance, milk or jade or even your ear. You can see that especially in movies when they have strong lights behind them. You see like light going through the ear and the light becomes like orange, reddish. This is exactly what's going on here. So we're going to ignore the act of scattering and going through the object because it's complicated. It's really hard to implement in real time. It's possible. There are tons of approximations we can use. That's how skin is done in games, for instance. And we're going to focus on the top part of this picture. So it's called the BRDF. the bidirectional reflectance distribution function. And really, a VRDF is made of two components. So in the lighting that you see, all the light that's reflecting, that's bouncing off of materials around you, there's two parts. There's the diffuse part, so that's the green arrows, and there's the blue part, that's the specular part of the light. And we're going to take a look at the difference between those two and explain why they're important. So earlier I mentioned there are two types of materials, roughly. We're simplifying a lot of things here. Conductors and dielectrics, or in more friendly terms, metals and non-metals. So could anyone here tell me what is the difference between a metal, like a metallic surface, and a non-metallic surface? What makes a metal look like a metal? Do you have any idea? Reflections, okay, but in what way? You get reflections, but I have reflections on my leather wristband. So the answer is here. So this is, so the actual surface response of an object is the following. So you have the light incoming, it hits the object. Some of the light will be refracted and scattered inside the object. If the scattered light comes back out, that's the diffuse light. So that's what gives an object its color when it's not a metal. And some of the light will bounce off directly, and that's the specular part. So those are the reflections. And when you have a dielectric object, so a non-metal, you're going to have a diffuse component. Metals do not have that diffuse component. So in the case of metals, some of the wavelengths will be absorbed directly, but they won't scatter and come back out. So you're only going to have reflections. So if you take a piece of metal and you look at it in the dark with a light that's far away, you probably won't see the metal at all because you're only going to see that tiny reflection. So like I said, conductors, they only have reflections, and they don't have a diffuse component. So let me show you a demo. We're going to switch. So that WebGL demo, I can run it in a slightly different mode where we can play with the different properties of the materials. So here we have a very simple plastic ball. So this is a dielectric. So we can see there. It's hard to tell on the screen, but there are some reflections coming off of the environment. You can see the specular reflections. And all the red that you see, that's the diffuse part. So this is a red plastic. Now, if I make the object become a metal, you can see that we lose all the diffuse component and we'll only have reflections. So we only see what's reflected off of the environment, which means that if I turn off the lights, I remove the environment, we only see the reflection of a light that I have close to the sphere. If I turn that off, it's also gone. So if I go back to a dielectric, you can see that even without the environment, we still get a lot of diffuse light. We still get a lot of red coming off of the object. So that is the main difference between the two. And as you can see already, I mentioned earlier that with PBR, it's easy for people who are not artists to create objects because you think in terms of physical properties. Like if I were to create a material, I have to think, is it a metallic material or is it a non-metallic material? And suddenly it becomes a lot easier to create those textures because all I have to put in the texture is 0 to say it's not a metallic object, or 1, it's a metallic object. And then you can create very complex textures where you could have painted metal where the places where there's paint on the metal, it's not metallic, but if the paint was scratched off, you can set that to 0 and say, okay, that's not a metal anymore. So I mentioned the microfacet model, and the way we think about surfaces, what you saw in the slide in the previous diagrams, is completely wrong. So surfaces are never completely smooth at the surface. So this is usually how we think about any surface really, but this is what happens actually in real life. Again, it's a gross simplification, but it's the concept of thinking in terms of microfacets. So your object is full of very, very tiny. You could think of them as like little rectangles that can reflect the light. And as you can see in this diagram, like when you have different rays of light that arrive parallel to the surface of the object, they can bounce off in different directions depending on the distribution and the orientation of those facets. And that's something called roughness that we're going to look at very soon. And if you zoom in closer on those microfacets, things get even more interesting. So here in green, we have what we call the macro surface. So if you create a mesh, like that little spot you just saw earlier, that's going to be your triangles. And we're going to use just mathematical equations to simulate a distribution of microfacets at the surface. And the way the distribution works is we want a probability for the light to hit a facet whose normal is halfway between your eye and the light. So the more facets you have that have this property, the brighter the surface will look, or the less rough it will look. Even when a microfacet reflects light, we can have two phenomena happening. There's masking, so the light bounces off the facet but gets blocked by another one, or a facet will cast a shadow on the facet that's bouncing light off of the surface. So we need to take that into account as well. And when you take into account all those properties, we use a single value to represent the distribution and the orientation of all the facets. It's called the roughness. So you can think of it this way. When an object is not rough at all, when it's very glossy, you're going to have really sharp reflections. So that means that all the light that's coming in will come back out in the same direction. The rougher the object gets, the more random the bouncing light will be. And we see that like those non-parallel rays appear blurry to us. So that is the difference between the various objects that you have around you. So a can of Coke is a very glossy object, so all the microfacets are oriented more or less in the same direction, but the floor right here is extremely rough, and the light is bouncing off in a very random direction. The other one is harder. So the first one, the diffuse component, there was a very smart guy called Lambert who took these equations and said, haha, I'm going to make it super simple. And that's what he came up with. So sigma divided by p, sigma is the color of the object. So all you do is you take the color of the object, you divide it by p, and ta-da, you have the BRDF for the diffuse component. So that one is super easy. And it's been in use for a long time. It's not perfect. It doesn't take the roughness into account. But we are pretty bad at judging the diffuse light coming into our eyes. And so most of the time, people just use this one. There are more complex models. Disney, for instance, uses a slightly different model, but they're not really worth it, especially in real time, especially in VR, especially on mobile. And the specular BRDF, so the one I've been using, and it's the one that's in use in Unreal Engine and Frostbite 3. Frostbite, for those of you who don't know the name of that game engine, it's the one that's powering Star Wars Battlefront or Need for Speed for recent games. So this is what the Cook Torrents BRDF looks like. Again, don't be too scared. I'm going to talk about those components. We're not going to go into too many details. I won't show you what's behind those terms. So we have D. The term D is the distribution of the microfacets. That's the probability that they're facing you, basically. F is the Fresnel term. It's a French word, so I'm going to pronounce it in the French way. And we're going to look at this one in a bit, because this one is really cool and very important. And G is the shadowing and masking part of the behavior of the surface. So remember when I said that the microfacets can shadow each other? That's what this term does. It's another probabilistic term. We don't need to look at it in details. Just talked about all that. Yeah. So if you're interested, at the end of the last slide is just the name of all the papers that you can go read if you want to recreate all that yourself. And they're extremely interesting. Just to help you, so we saw that the BRDF is D times F times G divided by 4 times 2 dot products. Very often what you're going to see in papers is that the G and the 4 and the dot products are combined together to form a term called V for visibility. And so the equation just becomes D times F times V. It just makes it a lot easier once you're told that this is the case. Understanding papers becomes a lot easier. So quick demo. So if we go back to our editor, so here we have our plastic ball. And if I change the roughness, you can see how we make the reflections blurrier. And same thing if you take a metallic object and you change the roughness, you can see how everything becomes blurry. So again, really easy, if you want to create, I don't know, something mirror like a car of a very low roughness, they reflect off a lot of light. But frosted glass, this ground will have high roughness. And with just those 2 parameters already, or 3 parameters, the color, the metallic, and the roughness, you can create all the materials I showed you earlier when I was switching the materials here. So if I use like tiles, all it's doing is applying textures that encode for each pixel the color, the metallicness, and the roughness. That's all you need. You don't need much more, and you can have something that looks really, really good. So this is what's really appealing to me. The PBR is really appealing because you can create very complex objects visually, and yet it's very simple to author. So I mentioned the F term, the Fresnel term, from Augustin Jean Fresnel, a French physicist. And it describes how the light behaves when it moves between two different media. So for instance, when light goes from the air to the surface of an object, that's moving between media. So typically, it's the index of refraction that you care about. I'm sure you've heard about it in school as well. So there are different indices of refraction when you go from air to water, from water to crystal, or whatever. The two that you really care about are moving from air to a solid object, it's 1.5, and moving from air to water, it's 1.3. And what's really interesting with the Fresnel term is that it describes something that we see every day without thinking about it. The amount of reflected light increases with our viewing angle. So you can see that with water really well. So imagine there's a pool of water in front of you. So if you look at the pool straight down, you're going to see through the water. But if you lie on your stomach and you look at the water at a grazing angle, you're going to see only reflections. And as you get higher and higher to look at the water straight down again, you're going to start seeing the water will appear more and more transparent. So this is something that happens everywhere around you. So it happens on the bricks, on that can of Coke, on the chairs. It's not just the water. It's just easier to see, like on large bodies of water or something else. But it's all around you. And adding that to your renderer makes a huge difference in terms of quality. So let's look at our objects again. So you can see the Fresnel in action on the side of the object here. So let's see if I make it. So here in the middle, it's a little hard to tell, but the reflections are very dim. You can barely tell that we're reflecting light off of the environment. But if we move to the sides of the object, then the reflections become very obvious. And on top of that, it's a little hard to tell here, but I'll show you a photo that explains that in detail. So on that plastic sphere, all the reflections are red, appear red because the object is red. But the more you move towards the side of the object, the less they are red, the more they become achromatic. Again, we'll look at a picture because it's hard to tell on this screen. So this is the actual measured Fresnel data for different materials. So this is the viewing angle here. So when you're here, you're looking at the object at 0 degrees, so like you're looking straight down at the water, for instance. And at 90 degrees, you're at a grazing angle. And what we can observe is that no matter what material you're looking at, they all converge to the same point here. That means that at grazing angles, they will all have perfect reflectivity. They will all reflect all the light, and they will, and the reflections will lose their color and just use the color, the original color of the environment. Fresnel, there's basically two parts of it. All the objects that are non-metallic have a very low reflectivity index. So for most objects, it's going to be around 0.20, actually here, 0.04, like 4% of reflectivity. And metals have a high reflectivity. And metals also are colored. So you don't have to worry too much about this one. We have a very good approximation. So this is a photo I took of my Christmas tree. I was on my way out to fly to Michigan, but I saw that and I couldn't help myself. So this is the Fresnel term in action. So we have a green metallic ball, and you can see that on the edge, I was lighting the ball with my phone, and you can see that on the edge, the green disappears, and we start seeing the red that's coming off of my screen. So that is the Fresnel term in action. The more we go towards the grazing angle, the less colored the reflection becomes. So it's very easy to implement. Another French dude, apparently there's a lot of French people who do graphics research, called Christophe Schlick, came up with this approximation. So it's a fairly simple equation. So this is basically your viewing angle. You can ignore it. And we have two colors. There's F0 and F90. So F0 is what's called the specular reflectance at normal incidence. So for dielectrics, it's going to be achromatic. It's going to be just a percentage. So most of the time, it's going to be 0.04. You can ignore the rest. And for metal surfaces, it's going to be the actual color of the metal. So if you're gold, F0 is going to be yellow, basically. And F90, as we just saw in that graph, is always going to be 1 because the more we go towards the grazing angle, the more white the reflections are going to become. In previous rendering models, it was fairly common for artists to have to create what was called a specular color map. So they had to create a diffuse map that would contain the color of the object, and then they would have to create a second texture where they would put the color of the reflections. And it doesn't really make sense because it was very easy to get that wrong. So first of all, that's how you would end up sending back more energy than you would receive. And also, it was really hard to get something that looked natural because you would basically have, like the artist had to basically implement in his head that equation, which doesn't make any sense. So instead, we can do it for the artist. So we introduced something called the base color. So this is the color that you want the object to have. So for gold, it's going to be yellow. For wood, it's going to be some kind of orange. And the way we compute it depends on whether or not you're a dielectric or a conductor. So for dielectrics, we're just going to use the base color directly. F0 is always going to be 0.04. F9 is always going to be 1. And for metal objects, the diffuse color is going to be 0 because there's no diffuse component. F0 is going to be the color that you want because there's only a specular reflectance. And F9 is going to be 1 as well. So this is a small chart that I used to create my object. So those colors, these are just interesting because they've been measured from actual real-world data. And you can see here at the top, when you select the color of an object, it's been observed that in the real world, all the metals, their color is always in that range of luminosity. So if you create a metallic object that has a value of like 50, 00, like you want something that's red but the dark red, you should not do that because that does not exist. Like it does not exist in the real world. Well, we let you do it because sometimes if you're creating a non-photorealistic scene, we should let you do whatever you want. But if you want to create something that looks realistic, never get out of that range. And there's something similar happening for non-metallic objects. They never go under 50 and they never go above 240. And it can be pretty difficult to author the base color in PBR because we never see that color. The real color of objects, that's not what our eyes see. We see the reflected light. So we see the light mixed with all the source lights around us. And it can be really surprising, especially to artists, when they have to create those colors because most real-world colors are very muted. They look pale. There's no contrast in them. So it's a very different mindset if they're used to creating textures for games. They really have to change the way they think about it. I mean, you can see here, for instance, sand. It's this very dull color. But if you plug that in and you let the lighting system do its job, then you're going to get something that looks really good. For those interested, this is the GLSL code for OpenGL ES3 that implements everything I just talked about. So I'm not showing the code behind the 3 terms that we show in the VRDF, but that should give you an idea that it's not that complicated, things like that. But most of the time, you can just use that value here. So image-based lighting, I mentioned that earlier. So this is the use of omnidirectional captures of real-world light information. So have you ever played with a photosphere on your phone? Okay, just a few of you. That's basically image-based lighting almost. So to do image-based lighting, I actually have a show and tell. So we take a photosphere, really, like a 360-degree picture of the environment, in HDR preferably, and we can then process those images to extract the diffuse light and the specular light that are coming from the environment and that we want to incorporate in our BRDFs to light up the objects. And this is how we were able to, remember in the demo when I was changing the environments and we could see the lighting adapt on the object. And that's because we followed that process. I can show it again real quick. So we have our red sphere. And if I change the environment, actually, let me make it white. Okay. And if I change the environment, we could go to a hotel room in Vegas. So that one's not interesting. We could go to space. There we go. So we're in space. I'll remove the light. There we go. So, and one more thing. Sorry. It's easier to see that way. Again, so here you can see that we're lit up by this nebula on that side. If I make the object metallic, we get specular reflections. And if I change the environment, let's see which one we want. Parking garage. There we go. So this is a really powerful system, and I mentioned earlier it's been in use in the motion picture industry for many years because that's basically how they can integrate special effects in the picture. So think of a Terminator movie. You have this like big robot, that's very shiny robot that you want to integrate in this room. So the way they do it is when the actors are done, they just take a picture of the set, and then when they render the robot, they can apply the exact same lighting that was used on the actors to make sure that the robot looks like it belongs in the image. And so we're doing exactly the same thing, just at runtime. So those are pictures of my vacation last summer. I bought two very weird-looking balls, one that's very reflective and one that's very diffuse. And I was taking pictures with my friends, and we decided to capture some of those HDRIs so to do image-based lighting. So there are different ways of doing it. You can use Photosphere on your phone. You can use there's this wonderful toy called the Ricoh Theta. I don't know if many of you know what this is. This is awesome. It's like $200, and there's one button. You press the button, and you have a 360-degree picture stored in there. So if you want to capture those images to recreate the environment lighting, you just take a few to have HDR information, and then you can feed them in the tool, and you get all the lighting information. So it takes literally seconds. So we were like, in Vegas, in the middle of the strip, like with this on the tripod, trying to take pictures, annoying everybody. This is another way of doing it. This is the old way of doing it, where you take, it's extremely confusing, but when you take a picture of this chrome ball, all the information is there. Like in that single picture, we have 160 degrees worth of information, like even behind, on top, everywhere. The only issue is that some of the information is really compressed in just a few pixels. So we used a special camera, so that was a 60 megapixel picture, and even that did not give really good information. So usually what you do is you take 2 or 3 pictures around the sphere so you can spread out the information error. Those are called, you can actually buy those on Amazon. They're called gazing balls. They're supposed to be decoration for your garden. I guess some people like to gaze at chrome-looking balls in their garden. That doesn't make any sense. Usually found with like gnomes and things like that. And then you can just drill a hole and mount it on a tripod, and they cost like $20. This one is a little, those are hard to get. They're custom made for the VFX industry. This is a diffuse board. It's used to capture the diffuse information of the environment. So typically you would use it to subtract the diffuse lighting. It's very complicated. Don't worry about it. Just ignore it. But in the end, so when we process our environment capture, what we want to end up with is a cube map. So cube map is this cross format, and we can feed that to OpenGL, and that's how we can draw the background. That's how we can create the reflections. But then we're going to do a couple things to that cube map. So first of all, we're going to do this, and I'm not going to go into the details because it's extremely complicated, and it breaks my brain every time I think about it. Yeah, so whatever. And we need to separate 2 different components. So we need the diffuse information and the specular information. So the diffuse information looks like this. There was a river canal in LA, I think, the person who took the picture. So you can see like where the sun is. There's a lot of light. There's a lot of white light. The sky, there's a lot of blue light, and at the bottom there's a lot of concrete colored light. It's very blurry. It's not a very interesting image per se, but you'll see at the end why it's so important. There's a way to not have this image at all. We can use a mathematical tool called spherical harmonics to approximate that. And spherical harmonics are really wonderful. So the image you just saw, we can replace it with just 4 colors. So we can just have 4 RGB colors. And if they've been computed correctly, you can apply this code at runtime and recreate that whole image. So here's an example of the image we just saw with spherical harmonics. And this is important when they do that in games, or they used to do it in games where those papers, and then I discovered that they fake everything, and everything is really wrong. The split sum approximation, the idea is that you have a sum of products, and you say, well, that's the same as a product of sums, which is completely wrong mathematically. But it's good enough, it works. Recently, I did something similar myself. I was really proud of myself. I had the sum of squares, and we had the square root of that sum. I said, oh, there's a square root and there's a bunch of squares, so let's remove everything and keep the sum. And it's really wrong, but on screen, it looks the same. And it's a lot cheaper. So cheat as much as you can. And so the cube map we use for the reflections that you saw like in those spheres I was showing you when we changed the roughness, the way we get those blurry reflections is like this. So we have a cube map, and we create a MIP map of the cube map. So every level of the cube map is a smaller version that's been blurred. It's not the blur that you find in Photoshop. It's a blur it's an integration of the environment over a solid cone angle. Again, very complicated. I won't bore you with the details, but in the end, that's what you get. And it's just an image that you can sample from your OpenGL shader. Finally, so the way the idea works, we have the diffuse part of the image, we have the specular part of the image, the reflections, and when you combine the two, that's what you get. So I showed you those four colors with the spherical harmonics. So when you apply them to a sphere, this is the kind of result you get. And because diffuse light is so blurry, it really works. It's like this is a picture of Monument Valley, so you see the red sand at the bottom, and you see the blue sky at the top. Okay, now aliasing. So there are different types of aliasing, and unfortunately, there's really one we think about usually. The first one is texture aliasing. That one is easy to deal with. Then there's geometry aliasing. That one is the one that's the most talked about. It's actually pretty hard to deal with efficiently. And finally, there's shader aliasing. There are other types that I'm not going to talk about here today. So texture aliasing, this one is easy, might be difficult for you to see, but this is what happens when you have a texture that's seen at a grazing angle. In the back, here you can see that we're losing information, so there's random pixels lingering around. So when you move the camera, it's going to have a lot of shimmer and flicker. Like any high-frequency details, like the text, will look terrible. So there are different ways we can deal with it. There's bilinear filtering. That basically blurs the picture by doing an average of the pixels. It looks better, but it still has quite a bit of aliasing issues. Then we have trilinear filtering, where the idea is that we build a MIP map chain. So we build a pyramid of images that gets smaller and smaller. And depending on the viewing angle, roughly, we pick one of those images, and that's how it gets blurry in the back. So it gets pretty nasty, but at least it doesn't have this scrolling effect that you see. And oh yeah, and I should say, like, finding aliasing is very important, especially in VR, because when the screen is in your face, all that flickering will really take you out of the experience and contribute to making you sick. And finally, the best one is called anisotropic filtering. This one uses partial derivatives on the GPU to do a lot of samples. And it's basically the best way to fight it, and it looks really good. It's pretty expensive, especially on mobile. So if you were to use it, you should use it only on very specific textures where you really, really need it. If you're on desktop, like, you should probably just use it no matter what. So geometry aliasing, there's two types of solutions. You can increase the sample rate, and some of the techniques include, the names are really weird. So this one is ordered grid, super sampling anti-aliasing. This one is full screen sparse grid, super sampling anti-aliasing. There's multi-sample anti-aliasing. There's coverage sample anti-aliasing. And this one, I forgot, that's from AMD. The first two, they're the easy way out. Let's say you need to render an image at 720p. What you're going to do is render the image, let's say, 16 times bigger, and then just scale it down when you compose it on screen. So this is really efficient. It works really well in terms of quality, but it's extremely inefficient in terms of power that you need on the device to run it. So on mobile, just forget about it. In VR, also forget about it. MSA works really well. We're going to talk about it just a little bit. This is probably the solution that you want to use because it's really fast and it's super easy to implement. It's literally a couple lines of code. There are analytical solutions. So those are the solutions that are very common in games today. There's one called FXAA, and I forgot what it stands for. Pardon my French, but it looks like shit. That's what you see in most games on consoles. And those are analytical in the sense that you first render everything on screen, then you run this filter where you try to find the edges, and then you blur the edges. And it's terrible because as you move the camera, the edges are going to move around, and the filter is not going to find them correctly, or it's going to treat them differently. and it doesn't work that well, at least in the cheap versions. That's morphological anti-aliasing. Then we have sub-pixel morphological anti-aliasing, and that one is temporal anti-aliasing. There are many more. You could write entire books about anti-aliasing. It's extremely boring, but suffice it to say there are many solutions to that problem. So the one we're interested about is MSA. So really the problem, like the reason anti-aliasing happens with the geometry is that when you render a triangle, let's say we have this red triangle. We're only going to color the pixel in red if the triangle touches the center of the pixel. And of course, as you move the camera around, like the center is going to move, and the triangle might be really small, so the pixel is just going to turn on and off as you move. So the solution with MSAA is instead of using just one point in the pixel to determine if you should render that pixel, is to use 4 points or more. So if you say I use MSA 4x, that means we're using 4 points. So in this case, because the triangle is touching 2 pixels, we're going to render the pixel red, but we're going to do 50% red. If we were to touch 3 samples, we would do 75% red. So the higher the MSA sample rate you use, the better. The nice thing is, it's only going to do this when you rasterize the triangles. So your pixel shader, where usually you do a lot of work, is only going to run once. So it's fairly cheap. On mobile devices, so if you're on a Qualcomm GPU or an ARM GPU or an Imagination Tech GPU, basically anything but NVIDIA, the cost of enabling MSA is going to vary depending on what you do exactly, but it's between 1 and 5% of your frame rate. Not of your frame rate, of your frame time. So it really isn't that much, and the quality is going to be really awesome when you turn it on.
So it means it's something you enable for the whole scene?
Yes, so MSA, it's something you enable for the entire scene. It's because you have to allocate buffers slightly differently. It takes up a little bit more memory, but it's manageable. So this is a comparison of the demo I just showed you. So we render a monkey, and this is without anti-aliasing, so you can see this stair-stepping effect that you might be familiar with because you've seen aliasing before. And with MSA, it might be hard to see for you, but we see like a slight gradient instead. So it looks better. The problem with that is it's far from perfect. So it works pretty well in this case because we have a very diffuse object. We don't have specular highlights. But when you do have specular highlights, MSA cannot do much for you. So let me zoom in on. Can I zoom in? Let me enable that real quick. Accessibility. There we go. Right. Yeah, it's a little bit hard to see. Let's go look here. So here you can still see a lot of jaggies. And this is really because MSA does an average of the samples. And the problem is that when you have highly specular surfaces, you can have one pixel that's going to be really bright and one pixel next to it that's not going to be very bright. And the average, it's still really bright. So it looks pretty horrible. So one technique we can use is called geometric specular aliasing. And it's been discovered, rediscovered, used in a bunch of games. Valve recently talked about it again in one of their talks about VR. But so the idea is to basically try to figure out what is the local curvature of the object. And the more curvy the object is, the rougher we want it to be. Because remember from the previous demos, when you make the object rough, it gets blurrier. So the idea is really like, okay, we know that here it's gonna be an issue because we have this big curve. So let's make it blurry right there. And it's very easy to do so. So this is the code, just a tiny bit of math. We use partial derivatives. I won't go into the details of why, but yeah. So the derivatives on the GPU give you the rate of change of a value. So if you take the normals, the derivative will tell you like, by how much has your normal change compared to the pixels next to you. So we can convert that to a curvature value, we turn it into a roughness, and then we use that on the object. It's very cheap, very easy to implement. And so this is just a visualization of what it looks like. So here I'm rendering the local curvature of the object. So the wider the pixel is, the more curvy the surface is at that spot. So you can see, for instance, here on the wheel, like where we change, like when we go from flat to the rest of the tire, it becomes white because there's a lot of curvature at this spot. And when we, so I hope you can you see the difference, the before and after? So if you look closely at the mouth or the ears, you should be able to see the effect of the geometry anti-aliasing. So really what we're doing is we're spreading the highlights. It's fairly visible here in the mouth. See there's this highlight here that becomes very blurry. But it gives a very, very good looking image. It's a little bit soft, but it's very pleasant and very stable. When you move the camera around, you don't see that flickering anymore. So as I was working on the slides, and this very morning, there's this Sir Kaplanian from Nvidia that released a new paper about this exact same issue, except instead of solving the problem empirically like I just did, he did it in a real way. So I looked at the paper, and I had to read it fairly quickly. It's a solution that's really, really good. It's much better than what I just showed you. It's also very expensive. It needs to be computed once per light that lights your object, whereas the previous solution is just once for all the lights. And it requires a feature called fine derivatives that is not guaranteed to exist on mobile with the current OpenGIS 3.2 version. So you could take a look if you're interested, but I don't think it's worth it on mobile at this point. Are we on time? I'm going to skip that one. Okay, so when should you use geometric anti-aliasing? Always, if you can get away with it in terms of performance. If you cannot, it's a property you can enable per object or per material. So if you know that you have an object that has a lot of curvatures, or if your object is very shiny and very curvy, then you should enable geometric anti-aliasing on it. But for instance, on the flat ground, this technique is going to do absolutely nothing. So you're just going to be wasting cycles computing that value. One last thing, so if you do use MSA, because it's so easy and it looks good, and if you do use HDR, a common mistake is to apply MSA on the HDR buffer. So the HDR buffer contains values that have a very wide range. And the problem is, like I mentioned, we're just doing an average of those values, and it's going to look pretty terrible. So the idea is that you first need to tone map, then do the result for MSA, then inverse the tone map, and I'll show you what it looks like. So this is MSA done wrong. So if you look here, you can see like a faint result of anti-aliasing, but it still looks like, you still see this staircase effect that looks pretty nasty. And if you do it the right way, you get this nice smooth line. And just a matter of changing when you do things in a renderer. Then we have shader aliasing. So that one often comes from, like, it could be because of the way you're doing your shading, but very often it's because of your normal maps. If you have high frequencies in your normal maps because you want to create something like concrete that has a lot of like little things happening at the surface, under minification, so when you zoom out, when you see the object like at small size, we're going to lose a lot of information. So what's happening is, this. So here we have a normal map where all the normals are pointing up, and we create our MIP levels. And the last one is going to be the average of all the normals in the texture. So it's going to just go up because that's where all the normals go. Now, if we do the same thing with a high-frequency normal maps where they're pointing in a bunch of random directions, chances are that when you do the average of all those normals, you're still going to have a normal that's pointing up. So what happened here is we had a flat surface, and we have this very rough surface with high frequencies. And yet, we're going to shade them in exactly the same way because we did this averaging in our textures, and we're being told that they're the same, but they're not the same. So we lost basically the roughness information. Remember, the roughness is whether or not the surface has a lot of normals pointing in different directions. So we can recover that information. And so here's a video showing the prime in action. So this is a very high-frequency normal map on the ground, and you can see like this flickering and shimmering of the light as I move the camera. So what we can do is take the normal map and then modify our roughness map. It might be hard to tell if you're in the back, but basically it's the same idea as with geometric specular anti-aliasing. We're gonna make the object rougher where we know that we have a lot of frequencies, like a lot of details. I won't go into the details, we can look at the papers, but this is the same scene once we've modified the roughness information according to the normal map. So it's a lot more stable. And you can see the before, after, before, after. Finally, there's something called diffuse aliasing. So the idea is it's very similar issue. So when you light an object, this is the lighting equation. That's your VSDDF. That's the amount of light coming from the light source. And that's the angle between the normal and the light source. And the problem here is that it's this part right here. So I just talked about the problem of averaging the normal. So what happens when we run that code, this normal here is the average of all the normals for our object. And this is obviously wrong because the average will change a lot when you move the camera around. So the idea here is instead of using this normal, we want to take the integration of all the normals. Again, I won't go into the details because you probably don't care that much. But here's the before, and here's the after. So here you can see that you have a lot of, it looks very grainy. And when you move, if I were to move the camera, there will be a lot of flickers and sparkles, and it will look pretty nasty. And here we have something that's a lot more stable. And it may feel like it's wrong because it looks so different, but when you compare it to reference renders, this is actually the correct version. Yeah, and there's so much more I would love to tell you about. If that's something you want to chat about, just send me an email. I'll be happy to talk your ear off. And those are all the papers you can refer to if you're interested in this topic. I'm gonna leave that slide on screen for a little bit. It's not zooming. Useless. Okay. Any questions? No, I bored you all to death. All right. Yeah. Yeah, I'll try to publish the presentation somewhere. Just look for my name in my blog, and I'll try to put it online as soon as possible. Okay. Yeah, and there's the video.
Why would you say this technique has become popular now and not 1 year before?
The reason it has become popular now is a combination of finding the right approximations and getting enough power. On previous generations of console, like if you take a PlayStation 2, for instance, there's just no way you could run all that math. If I were to show you the shader for that thing, I mean, when you have the real shader with all the lighting information and all the work you have to do to make it work, it's hundreds of lines of code. It's not, I mean, there's nothing hard in it, but it's just a lot of work for the GPU, and running that just takes power. The good news is that it does run on mobile. So our mobiles are powerful enough these days that we can actually do this. The other thing that's become interesting is that we've developed a lot of temporal solutions and also filtering solutions. So if you have very good anti-aliasing, what you can do is instead of rendering at the native resolution of your device, and consoles do that a lot, you render at a lower resolution, but you render a really stable, really clean image, and then you just stretch it. And most of the time, you won't tell the difference. And if you want to convince yourself it's a good idea, just take a Blu-ray, play the movie, pause the movie, and tell me if the image is sharp. Like, the answer is no. Like, what we've done for many, many years, especially in games, is we try to have these really sharp images, and it's actually wrong. Like, even when you take photos like with really good cameras, the world is actually fairly soft. For instance, you never see like those high-frequency highlights that I showed you in those videos showing the problems with specular aliasing. You never see that in the real world, pretty much, unless you like somehow found a ground made of like bits of diamond. But what's around us is pretty soft. And also, people started caring. That helps. Any more questions?
Do you plan to open source your demo at some point?
Do I plan to open source my demo? Yeah, I'd love to. I just need to make it happen. But there's a lot of material out there. Like, there's more and more you can find. And if you want to see, if you want to play with PBR online, there's this website called sketchfab.com. It's basically a website where artists can expose their meshes and their textures. And it's all PBR-based, so you can open like any one of the assets. Like, it's basically a gallery of really good-looking PBR objects.
I'm interested by the shader. But
yeah, send me an email. I can share stuff with you.